Hello everybody, I'm Alberto Massidda, and today we are going to talk about teaching machines to read code changes and actually to tell what happened. So predicting a commit message with neural networks. Just a brief word, I want to thank my company who sent me here, provided all the hardware for the training, for running experiments, providing the time for me to run the experiments. And we basically are a consulting company completely devoted to open source, which is pretty cool. And we only use open source technology. And we are an Italian-based company. We do DevOps, cloud, ML, big data, and lots of interesting stuff. So, why would we want a commit message suggestion? And is this presentation actually? Seriously? Well, okay. What do you want a commit message suggestion? For example, because we want to just help the developer, for example. So we want to give an ad to the developer. Or for example, we want to catch bad commit messages. Just imagine if your Jenkins pipeline was able to reject pull requests based on a lousy commit message that was attached. I think we all been there, right? So it would be nice if we had an automated way to generate stuff, to use it as similarity metrics and how good a commit message is. What we don't want, anyway, is a message based on templates, because message based on templates just suck. They can just tell you a very, very narrow cases, and we don't want just a nice crafted message where you fill just names. Instead, we really generate a message which pertains the very specific case you're tackling. And we don't want also a message that summarizes what has changed, because what has changed is trivial. This file changed in this way. This is the point of the git patch, the git diff message itself. Instead, we want a message that captures the high, at least the medium level intents of the coder and why it changed, okay? So it turns out that generating a message for a code change is a problem of summarization. And we want to generalize what was the intent of the coder, at least at a low level, why he did that. And maybe we are not exposed to the high level of the project because you cannot even tell it by looking at the commit history, but we want to know what is changing in that particular context. A change of code always comes with a commit message which describes the full change. So in essence, when the developer writes a commit message, it's generating a summary of the changes. And we want to exploit particularly this thing. Diff patch provides a really focused source of code to summary mapping. So in this case, we change only this line, and we replace with this, and this one is being copied because I want to generalize for multiple items. And so the point of the learning in this case is learning a code to summary mapping. What can we use for that? Neural networks. Neural networks are particularly good at generalizing mapping from source to target. And machine translation can actually help a lot, because the whole point of the statistical machine translation and later on neural machine translation nowadays is to infer a mapping between languages. And by means of counting the co-occurrences of words between two different parallel corpora, or vector embedding manipulation. What I mean is that if we take a sentence and we map it into a dense vector of float numbers, right? Much like we do with the TF-IDF in information retrieval thing, and we put it into a multidimensional space, in a high dimensional space, like 256 dimensions. Concepts that will be really near will be near in this space. And this holds true across different languages. So we can map from a language to another by looking at vectors, at concepts that sits near in the language. So in order to do machine translation, we need an architecture first and a data set. The architecture that we picked in this case is the Google Neural Machine Translation architecture, which is the state-of-the-art for the machine translation. Basically, it is a sequence-to-sequence model with attention. We have here the inputs, and are fed into a bidirectional recurrent neural network with LSTM cell in order to prevent the vanishing gradient problem, which is the phenomenon by which the neural network tends to forget what is seen in a state which is far into the computation, and so it's not able to learn. Then we feed this double pass, forward and backward pass, to a stack of 8 layers, which have also residual connection. Residual connection is when you just, you not only feed the input of previous layers into the new one, but you also feed the original input and you concatenate together. This is because it was observed that producing the intermediate representation of a result along with the input helps generalizing better, because the gradients, when you are back-propagating, flows across the residual connections and are not hampered, basically. Then you feed everything to an attention model, which is a nice machine that sits in between and helps understanding what is the part of the input that should be used across all the multiple words that you have been feeding in to generate the current state in a decoder. The decoder is the network on the right, which is the one which currently is really generating the sentences. Okay, so this one is getting the context of the diff patch, everything that has changed, the file names changed, the code changed, feeds into a decoder which generates, by means of a recurrent neural network, it generates the real words that will be fed. And also this one is a stacked 8-fold recurrent neural network with, is monotonic, it's not bidirectional, with residual connections. And then we needed a data set. So we used the commit data set provided by the Jiang and Macmillan experiment, which this presentation takes inspiration from, which was a research done 2 years ago about how to extract commit messages from diff patches. They used a totally different technology because they didn't have this at the time, so we are actually using better weapons to tackle the same problem. It's 2 million commits from the top 1,000 Java repositories on GitHub. We extracted only the first sentences from each commit message. So and then we basically stripped away the issuer, the commit hash. We tokenized everything with white space, keeping the camel casing and punctuation because it's part of the language. And then we basically had to cut out everything which was longer than 100 words, being in diff patch or being in the commit message. And this left us with 75 commits. And then we apply another filter, which was described in that experiment of 3 years ago by Jiang Macmillan, which was try only keeping the verb direct object messages. So if I take a bad commit message like blobs of code and then fix, I cannot really, and there's lots of them, I cannot feed it to the as a training sample because it will make my model produce garbage. So the best commit messages are those which begin with a verb, added this file, updated the changelog, I don't know, removed this kind of import. And then there's a direct object after that. So it really is a good message that summarizes. It was a very heuristic way to tell bad commit messages from good one and try to have a kind of unsupervised way to separate bad messages which should never be fed as a training samples. And so we left with the 32,000 commits split in 3 different sets. The biggest for training, then one for validation during one for testing during the training, and one for validation after training was done to prevent picking. We used the Sockeye, which is a deep learning framework for sequence to sequence, much like tensor to tensor, based on AWS MXNet, which is a really cool framework, by the way, even though it's really an underdog of the field. Everybody is just in love with PyTorch and TensorFlow. I like MXNet because it's really polished, they're really well designed from ground up. And the training happened of AWS itself over a Tesla K80 and a Tesla V100. And I want to spend a few words about the fact that the new GPU that NVIDIA released is a total beast. And it costs 4 times as much, but it's 4 times faster. So they say that the only thing that money can't buy is time. Well, in deep learning, this buys you a lot of time. And the original experiment was 38 hours training length. I ended up in 5 hours. So it really let me iterate a lot. And you can see that from the perplexity of the output generated during the training, you can see the model really picked up instantaneously. And there was no overfitting. This is the same graph over logarithmic scale. So you can see the model still has a long way in this apparently flat field here. And it's still really picking up. And it stopped by itself after entering that plateau. So the results, 5 hours later, which is 242 epochs and 43,000 mini batches, are these. And these are actual figures I ripped out from yesterday evening while I was frantically scrapping through my presentation to tweak it. So I removed these 2 lines. This is the human, the original commit on the validation set, so no peaking here. So remove no needed imports. The machine translation said remove unused import. So the machine really generate this message just looking at this one. And in this case, the messages are actually equal. So add the table of contents in Python README, and the machine said really the same. So this makes me think there's a kind of a repetition pattern in the training data. The training data was shuffled and was divided. So it should be really, I could not believe it like this because I thought the machine would have tweaked it a little. And this one is nice. Here we are updating the version of Gradle, and so update Gradle. And the machine said update the build tools version. So he knows that Gradle is a build tool, and he understood that I was updating the version actually. This is my favorite. So version 1.2.3 in the POM file of Maven plugin. Update the OS Maven plugin to fix an issue with IntelliJ IDEA on Windows. There was no way the machine could actually know that on Windows the developer had a problem. And so the machine said, upgrade the OS Maven plugin to fix the build issue. Because if you're fixing the POM file, it means that you have a build issue. And this is the actual plot of the neurons in the attention model. So, okay, let me just go through this. Here you can see the patch, the commit message. So it's everything like this, crammed in just one line, okay? And you can see here the message that was output, upgrade OS Maven plugin to fix the build issue. It's really crammed because this is a fixed representation graph, and so the labels jump one another. And here you can see that these are the neurons who got activated. So whenever you see blank space, you actually are seeing neurons that didn't fire up. So it's a matrix multiplication. So if you multiply your input in a matrix, you obtain another matrix as an output, or you obtain an output field. And so the neurons who actually have the highest score, they have activated, okay? Like this standard neural network stuff. And the neurons who have a low score actually didn't fire up. This is because there was no matching, like a template, between the input and the output, like the input vector running over the matrix, okay? So here we are plotting the real float numbers as in a grayscale. So the higher the numbers, the higher the correlation between this input and this output here. So you can see the upgrade OS Maven actually triggered when it saw artifact ID words and it saw Maven. And here, to fix the build issue, triggered a lot when it saw Maven. So Maven is a synonym for build issue, because if you're changing your POM file, it means that you have a serious problem building up. That's what the machine learned, actually. And the graph goes this way, because you start from the first word, which are the top already, and here. So the gradients falls like this. So was everything actually a success? Well, for those who are not acquainted with machine translation lingo, the metric that we use in machine translation is called BLE, which is a bilingual evaluation. I don't remember what it is, but the fact is that we actually compare the output of machine translation and a human translation, and we count the engrams, the words in common between the original and this one. It's scaled between 0 and 100. It's actually impossible to get 100 even for a human, because it means that you should have written exactly the same thing. So this metric is not very good, but it's a standard, and it tells you that if you have a very low BLE score, a low BLE score is actually 15, 10, your model sucks. If you have a high BLE score and the fluency starts to popping in at 18, 20. So for example, 26 is a nice BLE score, and state of the art, which is Google Translate on fluent language, is 34. The original experiments of the Giang Macmillan was 33. We obtained 37 because we were armed with a better architecture. And this is the character engram F score of 40, which is stellar. So precision and recall is 40%, which is really, really high. Watch out, if you get a too high BLE score, like 70, it means that something is totally wrong, because you're just copying, you're just feeding the validation input as a training sequence, so you cannot just learn that. So the model has learned fluent English. It outputs perfect English phrases, and it spotted very interesting correlations in short commit patches. So, okay, you talked briefly about history of success. Why do you talk about failure? Well, because then I said, okay, we are really using a very constrained data set. Let's just try to remove a lot of constraint and see how it performs of wild commits. Well, actually, I didn't get the very good results, because the error rate for long patches is embarrassing. A lot of sentences, although are good English, are totally incoherent with the input. And that's why the dataset is so picked, so well chosen. For example, and I have a lot of this, the human, I won't show you the patch because it doesn't matter, but the human comment was change default FBO cache size to 0. Machine add and use and import for no pass. There was no pass thing anywhere. There was no imports. There was nothing related to that. So why is the reason? And these are the things that gets interesting. So you learn the most of the technology when you watch it fail. You know, you look at stack and trace and you know how the dependencies are doing. You see an edge case and you know better your model. So this turns out to be an extremely difficult task in practice, because vanilla machine translation architecture is not tuned for this particular task. So, for example, we have, when you're translating English to French, you have sentences which are kind of same length approximately. Actually, translating English to French is so easy that is basically not taken even into account, because it's too much of an easy task. Instead, we shifted towards English to German, because the formation process of the sentences is very difficult in German, which you concatenate stuff, respect to English. And but you have kind of a growing ratio, which makes the sentences not too much in balance. So 30 words against 40 words maybe, or 20, because you concatenate. Instead here, with diff patches and a pitiful commit message, you have an imbalance which is tenfold. And this is what leads us to the fact that the decoder is fluent, because the output is always within 10 tokens on average, 10 words. So you actually have a recurrent neural network which unfolds 10 times, and is able to generalize well and to output fluent English. But then you have very poor context performance. So if you output a very fluent English sentence which is totally incoherent with diff patch, it means that the encoder network, this one, remember, is not able to condition appropriately the decoder. So you're not able to capture any meaningful context to feed to a decoder in order to instruct it what should be generating. So it generates random fluent words. So totally gibberish, which looks like very nice English, but you're not conditioning. And not even a human can remember a 500 words context. And this is not about a vanishing gradient problem, because the LSTM is able to prevent that. But over a 500 length, it cannot just carry out enough context. And the attention model, who just is supposed to link the exact input word to the exact output word, cannot keep up with such lengthy inputs. And this is our fault, actually, because the diff patch, it's too complex. It contains insertions, ablations, context, things. And so we are just cramming together too much stuff. So this approach with this kernel architecture is just doomed to take so much further. Also, there are memory problems, because if you are unfolding 500 times a recurrent neural network, your memory will explode. So Google Neural Machine Translation works well. The transformer, which is the state-of-the-art in sequence-to-sequence model, goes out of memory instantaneously as soon as the training just begins. So I'm proposing here a better architecture. So the main source of chaos stems from the input length and the complexity, because we are cramming together insertions, so new lines of code in green, ablations, the red lines we are removing, and the context, the white lines that's just telling you where you are. It will make much more sense to adopt a multi-encoder network in which we use an encoder for insertion, one for ablation, one for context, and then a hierarchical attention network to tell which is the encoder which is not influent should be actually disregarded, and then just one decoder to funnel out everything outside. Which is much in the spirit of the transformer, actually, because the transformer is a sequence-to-sequence network which don't use any recurrent neural networks and just uses attention machines with multi-attention heads, 8 of them actually, attending at different parts of the code. And so you have different things, different moving parts, attending to different parts of the input and the output. And that gives it a lot of nice performances. So remember this, which you have a very natural way to separate context, because you know this is the ablation and this is the insertion. And everything which doesn't have a minus or plus is just context. So what I propose is that we get this very same thing blurred out, and we stash the lines pertaining to a context, no matter where they are, into a separate encoder, and the same holds for ablation insertion. We get an attention model in between, just to tell what are the relevant parts, and then we feed all these 3 attentions toward a global attention, and that goes into a decoder. The input complexity, the advantage is that it's factored into subparts. The speed is unimpacted because you have the same number of matrix multiplication plus 3. And same number, I mean 1 for each time you unfold. So if you have a 500 long input, you do 500 at least matrix multiplication. In reality, there are many more, because you matmul for the input, you matmul each time you compute a new step, and you matmul for the output, so 3 times. Instead, since you're factorizing the 500 in 100, 100, 100, it's 300 actually, you have the same number, you only add 3. And the precision is expected to actually improve a lot better. So instead of a traditional attention, where you actually take the source state, you do a dot product attention between all of these. Then you score them between 0 and 1 to say what is the state which is actually most pertaining to that current state. And then you sum together all these faded states except for the one which is the most pertaining, and you feed it to the decoder. I'm proposing to doing this. So you take the hidden state H0, you feed into the ablation attention and to insertion attention, for example, and you compute the weight against the ablation. So what are we supposed to get out of the ablation lines? Okay? How the current state, how the probability of generating the next English word correlates with the lines that were actually deleted. And you do the same for the lines that were inserted. And then you feed the two attentions into a global attention vector in which the inputs are not hidden states, but are the summation, the attention output. And in that global attention, you decide which is the next word that you should be generating based on the fact that you are seeing this ablation context and this insertion context. So no more about current just one single flat space, no matter if it's ablation or insertion. But you just factor out by hierarchically distributing the complexity. This is to be coded, of course, because it's a proposal, and it's a thing that I like to actually realize. It's not that technically difficult, actually. It's just a novel architecture. And this basically is the end of my presentation. You find everything in my GitHub repository, AgentI, vanilla neural network commit suggester. Everything is on the slides. You can download the website. Thanks everybody for your attention.
Okay, now we have about 10 minutes for Q&A. So, well, whatever questions you have, just make sure to repeat the question. So
sure. If you don't do any question, I will keep telling jokes. No questions? Sure, please.
I don't know if it's relevant, but is it possible to use adversarial networks for this kind of problems used for images, but
Okay, so the question was why, if it was feasible to use generative adversarial networks, which are kind of neural network architecture, in which you have two networks which play a game, one against each other. One tries to generate a nice sentence, and the other one has to detect if it was generated by a human or by a machine. And so you have a generator and a discriminator which tries not to get fooled by the other. And in the training, they compete to be better. And in the end, you have, yes, this is perfectly doable because GANs can be actually used for natural language processing. It will be a novel approach, which will make totally sense to try. They actually have a very different training scheme because they use reinforcement learning instead of vanilla backpropagation. But yeah, it will be totally nice thing. Please do. And come here next year to tell us how it's gone. Thanks. Another question? So the question is there any publicly available study which tells if there is a computer programming language which is handled best? There was a multi-language corpus in a study was actually about generating comments. And they gathered together different corpuses of code, so there were Python, there were JavaScript, and actually the performance was not too different. And in that case, it makes the difference having a very rich corpus, high quality corpus. So for example, I expect C code to be very high quality because the kernel messages, the commits in the kernel, Linux kernel repository, if you do a bad commit message, Linux Torvalds is going to bang your door in person and actually kick you very roughly. And so there is a kind of reign of terror which ensures that people stays in line and don't commit bullshit into the repository. So I just expect that if the project is serious, you will have nice training data and you will be able to generalize better prediction. Question? If I check it, if the commit messages fit. Please, can you please talk louder because it's very faint from here.
Have you looked into verifying whether the commit message is produced by the human
Yeah, sure. Here, the blue score actually was compared. Huh? Ah, okay, sorry. So the question is, have you tried verifying if the commit messages produced by the human, produced by machine, actually match those reversed? So, okay. The question is really tricky. So if I looked at the commit message by human, how they correlate with the actual code changes? Well, I can use this as a way to try to score the messages computed by humans. But there's the problem that I could get, if I use this kind of metric, for example, which is counts the n-grams in commons, so the subsection of contiguous characters in common of the sentences. So these two are very different, so these will get a low score, but actually they are pretty good. So it's really difficult to establish a metric to evaluate if the original message actually correlated very well to the commit change that you did. The same for this one, update Gradle. This will get a very shitty blue score, also because of the capitalization, which is different. So the n-gram will not fit. There was another message in which there was a typo in the original commit message, so update change log without the n, and the machine output update change log. So actually was able to generalize the correct spelling. That will get another low score. So it's really difficult to correlate the quality of the message, because the message usually is a low quality, and that's the whole point of coming out with this kind of Rube Goldberg contraption. Yeah, question?
As far as I can tell, the output, it would not be able to output anything it hasn't seen in the training set. Would it be possible to make it point to specific inputs that it maybe hasn't seen before?
Okay, so the question was, since you are actually trying to learning to translate between something that you've seen, right? How can you actually cope with things that you haven't seen? Well, that's the problem of out of vocabulary words. And neural machine translation suffers a lot from this because it's not able to generate a float vector of something it hasn't seen. So there is an effort is factorizing the words into subwords, and so that you can cope with n-grams. But generally, it does a good job because we use frameworks. So there's a lot of stuff which is in common different projects. And this tells us about the nature of software development, in which most of the code is not ours, but it's of the framework. And there are conventions, naming conventions, which helps a little. And otherwise, yeah, you get a rubbish thing which is not able to compute. But most of the times it goes well. And the very high blue score is very encouraging.
Okay, so time's up for questions. Thank you very much.
Thank you, so.